And so as a climatologist and as a meteorologist, I became more and more intrigued with water because it seemed to be so central to just about everything. But the more questions I asked, the more questions kind of all came back around to polarity. It's like every question, the answer was a description of H2O's polarity. But it didn't really satisfy me because the polarity was just simply just telling you that it had this one little characteristic where it had this tendency to stick. But even within that, there was a dichotomy because water is so fluid. So I was still kind of coming back to the same issue. I kept coming back to, why is water, if it has this high polarity, why is it so fluid? There must be an answer to that question. And so I was finding myself perplexed. And what do you do when you're perplexed? Well, a good thing to do is to go back to your first principles. And that's what I did. I said, hey, there must be something about polarity I'm not getting. There must be something I'm missing. So I went ahead and drew up this little picture here. And I kind of did a thought experiment. Now, keep in mind now, these are two molecules, of course. One of them is the H2O molecule. The other one is the methane molecule. Now, these two have a very important factor in common, and that is their underlying base structure, which is based on their steric number, and that dictates that the arrangement of the molecules on these, arrangement of the hydrogen atoms on these two molecules, both of these have hydrogen atoms, is the underlying structure is a tetrahedron. We can think of a tetrahedron as a three-sided pyramid with a bottom. It has four sides and four corners. And when it's represented on paper, it looks very two-dimensional. But if we were to actually twist these two oxygen around, that would actually indicate a tetrahedron. Okay, but we're not going to worry about that because we just have a two-sided sheet of paper. A two-dimensional sheet of paper here. But here's the thought experiment I did. I looked at this methane molecule and I said, well, what if I was to just moved these two hydrogen atoms away, wouldn't this turn into a polar molecule? And if you think about it, yeah, that makes sense because it has all the same characteristics that water does in terms of polarity. It has a electronegativity difference between the more massive carbon atom and the less massive H2O, and those will pull the electrons down. And because I had pulled these two away, it also became asymmetrical, just like the H2O molecule, which is a very important factor for why the H2O molecule is a polar molecule. So we could think of this carbon as literally becoming a polar molecule if you could pull those away. And then I thought, well, in a sense, you could vary these things. And as it got closer, the polarity would disappear, and as you pulled it away, the polarity would come back again. And then I thought again, I go, well, wait a minute, now if that will work for the carbon atom, couldn't we also imagine the same thing going on for the H2O molecule? You know, what if here you have other bonds coming up here and being made right here? Wouldn't that neutralize polarity when that happened? Think about that. And then I thought, well, wait a minute, would it really matter if the bond is covalent or if the bond is a hydrogen bond? In other words, if there's another H2O molecule here and it's forming a bond on this, wouldn't that, especially if, both places there, wouldn't that neutralize the polarity? Now in this case, the 0 here is indicating that this is an oxygen molecule, but normally this would have a 4 here. That would indicate that it has polarity, a delta 4. Now, think about that though. That's a profound concept. If H2O can form hydrogen bonds, wouldn't those hydrogen bonds neutralize the polarity in the H2O molecule the same way it does in the methane molecule? And that's really the big concept here, because I'm saying that that's exactly what happens with hydrogen bonds. Hydrogen bonds neutralize the polarity in the H2O molecule. And that explains a certain number of things that are otherwise very difficult to explain, one of those being why water is so fluid. Think about it. That's actually kind of an anomaly. It's one of the things that aren't really well explained. Why is water so fluid? Why, if it has these high, strong hydrogen bonds, apparently strong, or that's what we're told anyways, is it so fluid? Well, now we have the answer. The answer is because when hydrogen bonds are completed, they aren't strong. They're weak. Because the polarity, this actually neutralizes it, turns it into a nonpolar molecule, just like the methane. And that's the crux of this whole argument, that this is the reason why the H2O molecule has been considered so anomalous. This is what's so confusing. It's the fact that when hydrogen bonds are made, polarity is neutralized. And this explains a lot of the anomalies of H2O, maybe the most important of which is its high heat capacity. Because if you think about it, you now have a pendulumic effect right here. As something comes up and makes a bond, it's reduced to 0, but as it goes away, the charge comes back. Now you have a way of storing energy just in terms of the relationship between different water molecules within the liquid water. This explains that, and it also explains such things as surface tension, which I'm going to get into a little bit in my next video. Thank you.